All right, good morning. Here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. Today we're going to finish, or continue, not necessarily finish, but continue on with our study and analysis of Buckingham pi terms, learning how to find them, again, looking at some methods of using linear equations to find them, and using pi's, both linear equations, determining pi terms using both linear equations and dimensional or inspection techniques. So this is going to be the 24th video lecture in the series, and let us continue then. Okay, so again, continuing on from last time, dimensional analysis, we're looking at a basis of linear equations. So I want to look at finding pi terms using linear equations. Last time we used intuitive inspection method, but I want to look more at a method of using linear equations to find those unknown powers. Okay, so our general form, actually let me put this in terms of a subheading of linear equations. Using linear equations to perform dimensional analysis. Linear equations. Okay, so if we go back to a general form from the previous example of, or if you look at this in a general case, the general case for r equals 3 and r equals 3 reference dimensions, reference dims, and k equals 5 variables is something like this. Pi 1, where each variable is going to be an a, I could have something like a1 to the x1 times a2 to the y1 to the y1 times a3 to the z1 times a4, where each of these a's is one of our variables, like a could be density or a could be pressure or something like that, and pi 2 is going to be something of the order of a1 to the x2, a2 to the y2, a3 to the z2 times a5. I immediately know the powers of both a4 and a5. They're non-repeating variables. They're always going to be a power 1, power positive 1. So again, these are going to be our non-repeating variables, the ones that only occur once. Non-repeating variables. And then our a's, our a1 through 3, these are our repeating variables. And to me, this, kind of brings up memories of almost like chemistry class or something when I was looking at solving for reaction rates or something. That's what I make a mental connection of when I see this. But we don't really. What this comes down to is a method of linear equations. I see powers like this. I start seeing linear equations to solve for these powers. But maybe that doesn't necessarily make sense. But don't worry. We'll see what this kind of. We'll see hopefully how this will all work out. So again, we'll be using, we need to solve for these exponents. Exponents x1, y1, z1, etc. We need to solve for these exponents in order for the units to cancel out. All right, so I'm going to work through again with the I'm going to again work through the previous example, and we'll see how that works together. Okay, so from previous example, well, we use the equation delta PL, the drop in pressure per unit length, is equal to a function of diameter, density, so d, rho, viscosity, mu, and velocity, v. And then repeating variables, so let me break these down into repeating and non-repeating. The repeating variables and non-repeating and non-repeating. And non-repeating, well, let's look at the dimensions. Diameter has dimensions of length. Density has dimensions of mass, length to the -3. And velocity has dimensions of length, time to the -1. Then the non-repeating, delta PL, has dimensions of ml to the -2, t to the -2. Again, these are not units but dimensions. And viscosity has units of ml to the -1, t to the -1. All right, so I'm going to take these and I'm going to use these to actually sort of create some linear equations. It may not seem like it at first, but we can actually use these to create some linear equations. So, what happens if I apply my previous general forms here and plug these dimensions? If I plug the dimensions into the variables or into the pi terms, so I know that pi1 is equal to. I know that pi1 is equal to diameter times x, the previous variable x1 that I said, that's some unknown exponent, times rho times y1, times velocity times z1 times delta PL. However, what happens if I then substitute the dimensions into here? Well, I would get L to the x1, I would get m L to the -3 to the y1, and then when I plug in delta PL, that would be here, let's see, ml to the -3 times y1, and then for the velocity, I would get L t to the -1 times the variable z1. Finally, the delta PL will just be power of 1, which will be m L to the -2, t to the -2. Now, once all of this multiplies out, it must come to L0, M0, T0, or just 1. So you can start to see the origins of our linear equations. If I distribute these down, I can start getting some equations and relationships that will allow me to determine all of my other powers. So let's work with the pi one first. I'll work all the way through the pi one, and then I'll go back to the pi 2. Pi 1, I can break it down into each individual unit. So each individual dimension, not unit but dimension, must multiply together to produce a dimension of 0. So in other words, if I look at, I can use these to create certain equations. So L times x1 times L times -3y, -3 times y1 times L times L to the z1 here times L to the -2 must equal L to the 0. So if I distribute this down, look at the individual dimensions. All of these dimensions must ultimately add up to 0. So in other words, L to the x1 times L to the -3y times L to the z1 must equal, or times L to the -2 must equal L to the 0. And then from this, I can create a linear equation that says x1 minus 3y1 plus z1 minus 2 is equal to 0. I have an equation. So that is my first linear equation. x1 minus 3y1, again, this comes directly from the powers, plus z1 minus 2 is equal to 0. Then I can create a similar one for the mass. So m to the y1, times m here, times m to the first from our non-repeating variable, must equal 0. And so then that leads us to that y1 plus 1 is equal to 0. Therefore, y1 must equal negative 1. Basically, in our previous lecture, we solved this problem using just sort of inspection. We just sort of played with the variables and tried applying different random powers, and eventually we got something that would work out. This is a more systematic method. It's a bit more math involved, but it's more systematic in that you only have to do it once. You invert a matrix, you solve for it, and you're done. Or you don't even have to use a matrix often enough. But then I can look at the time. So t, and remember when we have a power like this, we multiply it down. So if I look at t, t to the negative z1 times t to the negative 2 equals 0. Or sorry, equals t to the 0. And this should also say m to the 0, sorry about that, m to the 0. And that leads us to that negative z1 minus 2 is equal to 0. Therefore, z1 must be equal to 2. And then if I know that z1 equals 2 and y1 equals negative 1, I can plug those into this equation here, and I can find that, let's see, that x1 will be equal to 1. If you plug these into this equation, so again, we get a positive 3 plus 2. Oh, wait, does that make sense? Oh, yeah, positive 3 minus 2.
Z1 should be negative 2.
Z1 should be negative 2. Oh, yes, thank you. Yes, so that would be positive 3 minus 4, so minus 1, bring it over here. Yes, x1 equals 1. And so then, if x1 equals 1, if y1 equals negative 1, and z1 equals negative 2, then pi 1 must be equal to d times rho to the negative 1 times v to the negative 2 times delta PL, or simply pi 1 is equal to d delta PL over rho v squared. And that is the first pi term that we determined previously. And that is the pi term that we determined previously. Okay, so now I want to do the same thing, but for the pi 2 term. So again, to review, we set up we took our basic equation. We said that the pi must be some power multiplication of each of the 3 repeating variables and the one non-repeating variable. Then we found the dimensions of each one, and we substituted those dimensions into the previous expression in replace for velocity, for viscosity, etc. Well, I guess not viscosity in this case. And then we set up a series of linear equations to find the powers necessary in order to make all of those dimensions have a power of 0 at the end. Let's look at this again, this time for the second pi term. So pi 2 is going to be equal to, well, d to the x2 times rho to the y2 times L to the, times v to the z2 times mu. And then if I plug in the appropriate dimensions, well, this is L to the x2 times, for density, mL to the negative 3 time to the y2 times LT to the negative 1 to the z2 times mL to the negative 1 t to the negative 1, the dimensions for viscosity. And all of this must equal L to the 0, m to the 0, t to the 0, or just 1. And then I can, if I distribute these down, and then look at each of them in terms of the three fundamental dimensions. If I first look at length, I can see that L to the x2 times L to the negative 3 y2. And again, when I create these equations, all I'm saying is that all I'm doing is separating out one particular dimension. These dimensions don't combine together. It's just like if you had, a, b times, all this kind of thing, but multiple powers of a and b, you could write an equation and solve for the power just using linear algebra. Times L to the z2 times L to the negative 1 equals L0. And so from this, I can get an equation that says, okay, x2 minus 3y2 plus z2 minus 1 is equal to 0. So that's one equation. Then if I create an equation based on the mass dimension, I can say that m to the y2 times m just to the first equals m0. And from this I can get very easily, I can write the equation y2 plus 1 equals 0. And this leads us to that y2 is equal to negative 1. So y2 is equal to negative 1. And then I can create a similar equation for our time dimension. T to the negative z2 times t to the negative 1 equals t to the 0. And that can, from this I can create the equation negative z2 minus 1 equals 0. Or simply z2 is also, that would be negative 1. And so then if I take this and plug it in here, I can get my power for, I can get my x2. So x2 therefore must be equal to 1. If I substitute this in here, that would be 3 minus 1 minus 1. So that would be just, okay, so that would be positive 3 and then minus 2. So what do I have? Dx2 would be equal to minus 1. Sorry about that. X2 would be minus 1. All right, so we have that now. And so finally I can simply say, okay, well, pi 2 is equal to d to the minus 1 times rho to the minus 1 times v to the minus 1 times mu, or pi 2 is equal to mu over d rho v. Is equal to d, or mu over d rho v. All right, questions on that? Okay, I know that's a lot, but hopefully you can review through this, and I mean, it is something to wrap your head around. It is something that can be difficult to wrap your head around, but conceptually it's really not that, but in terms of mathematics, it's really not that bad. All we're doing is distributing power, substituting things in, distributing powers, solving very, very simple linear equations. And for more complex problems, if you have a more complex problem, you might need to use a matrix to solve it, and invert a matrix, something like that. That's very easy to do using Excel or anything of that nature. So don't worry if I give you something on a problem like this. I'm not going to, on an exam or something like that, I'm not going to give you a problem that's so complex that you need to, invert a 3 by 3 or a 4 by 4 matrix when all I let you use on the exam is a hand calculator. That would be a little evil. So if I give you a problem like this on the exam, it's going to be of this level complexity, where the math is, it's simple, algebra 1 type stuff. So anyway, or solving the equations is, algebra 1, algebra 2 level math. So not too bad. So now I'm going to work through another example, this using a different type of system. Okay, so for the first time, I'm actually going to use something other than that stupid pipe with the pressure dot per unit for length. So we'll actually move on to a new system. And here, in this particular case, I am looking at the behavior of waves. So say I had a wave, a wave tank or something like that, and maybe I'll draw this as more a little bit neater. And this might have a certain velocity v. There might be a, let's say a wavelength L. Let's say there's a wavelength L, a height or a average depth d, and maybe there's a wave height h. Maybe a wave height h, plus various fluid properties. And given the following variables, h is wave height, v is wind speed, what would be driving the waves. So I'm creating some sort of experiment to model the behavior of wind and waves and the interactions therein. Let's say that rho A is the density of air. So this might be a bit longer than the previous one. Density of air. D is the wave depth. D is the wave depth. L maybe is, maybe not the wavelength, sorry. I said that was wavelength. Let's say instead L is the distance from shore. So maybe I can show shore here or something. Distance from shore. Although, again, for our analysis here, it's really not going to matter. We're looking only at dimensions anyway. Distance from shore. G, gravitational acceleration. So these are possible variables that we might want to investigate. And let's say that rho is the water density. And we're going to make this a little bit easier by just by outright stating what the repeating variables you want that we'll be using. So all this is given on this. Everything on this slide is going to be given. So I want to say that h, that is the variable I'm investigating, equals some function of v rho a diameter, or sorry, depth d. So v rho a d L G and rho. So density of air, density of water. And I'm also told to use d, v, and rho as the repeating variables. As the repeating variables. And I want to find pi terms to describe the problem. So I'm making things a bit easier for us by saying, well, we already know how to find pi terms. We saw that in the previous lecture. We already know how to, not pi terms, we already know how to find repeating variables. We saw how to do that in the previous lesson. So I'm just, to save us a little bit of time, I'm just outright stating, okay, this is what we're going to use for our repeating variables. Now, trying to do this all by inspection would be quite hairy. We have many different, for a set of repeating variables, for a given pi term, I'm going to have 4 different variables, the 3 repeating variables and another one of the non-repeating variables. And to solve for that, that's gonna take a long time to do by inspection. It would be much better to use a algebraic method if we can. So solution, this is going to take a bit of time, that's okay. Just another long form example on pi terms. Well, so again, we're going to use d, v, and rho as repeating variables. But first I want to check to make sure they're okay. So if we remember our conditions, the first is that we do not include the dependent variable as one of our repeating. So we didn't include that because h is not included. So we're good there because h is not included in our list of repeating variables. Then I want to make sure all reference dimensions are present. Well, let's see. D is going to have dimensions of length. Velocity is going to have dimensions of Lt to the negative 1. And density is going to have dimensions of m L to the negative 3. So we can see that m, L, and t are all present. All dimensions are present. Again, they do not need to be present in all of the variables, in each of the variables, but they must appear at least once somewhere in your list of repeating variables. Now, we do have to be very careful. It should be obvious that we can't use both row and row A as one of our repeating or as two of our repeating variables, because if we remember previously, we must not be able to combine them to combine two repeating variables to something unitless by themselves. Or combine repeating variables to produce something unitless. All right, so if we look at this here, well, there's no way I can do that. I mean, the time only appears in one variable, the mass only appears in one variable, there's no way I can really jumble these together by multiplying them, dividing them, taking them to some power, that these and these alone will give me a unitless term. There's just no way I can do that, and that's exactly what I want, a dimensionless or a unitless term. All right, so let's solve this using linear equations. So pi 1, well, I'm going to use, I'll let this be my first pi term and look here on the right side of my equation. So I'm actually going to need a total, if you run through that equation of the number of necessary pi terms, I will find that I actually need 4 pi terms to describe this problem. So the more complex the problem, the more pi terms you need, the more complex it becomes to find those. So in this case, even those 4 pi terms would be a little bit difficult to run experimentally, but it would still be a lot easier than the 7 or, wait, how many do we have altogether? We have 1, 2, 3, 4, 5, so yes, the 7. So in this case, we'll be able to reduce it from 7 variables to 4 variables. Still a big reduction, but that's still a lot. So pi 1, well, I know that pi 1 is going to be equal to d to the x1 times v to the y1. Now, what I do like about this method is that we don't have to reference the one pi term to get the other pi terms. We do have to run through some equations, but it's not like we have to run through, a whole bunch of equations, like 30 equations or something all at once. We're talking 3, 4 equations, something like that, on a single pi term. So d times x1 times v times y1 times rho times z1, actually only 3, no more than 3 equations now that I think about it, times h must be equal to, if I substitute in the appropriate dimensions, L to the x1, Again, my 3 repeating variables, these are the repeating variables, d, v, and rho will appear in each of my pi terms. The h and the other non-repeating variables will appear only once in one pi term. Times L to the x1 times Lt to the negative 1 times y1, or to the y1, times ml to the negative 3 to the z1 equals, times L, I should say, for our h. And this is all going to equal m to the 0, L to the 0, t to the 0. Then I'll construct 3 equations, one each for the reference dimensions. So if I look at for L, I can say that, from L, in order to make this, all of these L dimensions come out to 0, I basically have to say x1 plus y1 minus 3z1 plus 1 is equal to 0. Plus 1 is equal to 0. Or maybe just 4L, not from L. For M, well, if I look at M here, there is only one term with a z with an M in it, so I can just say, oh look, z1 is equal to 0. Very simple. And then for t, well, I have a t here, and that's it. So negative y1 equals 0, or just y1 is equal to 0. So, and if I put in the 0 for each of these, I can get that x1 must be equal to negative 1. So, for all of this, pi 1 collapses very quickly into a very simple term. Pi 1 is just going to be equal to h over d. So pi terms don't actually need to be that complicated. They can collapse down to something fairly simple fairly quickly. Oh, what did I do there? Pi 1 is just going to be equal to h over d. H over d. Next, I'm going to do the same thing. So I'm going to run through and do really the same thing for all of these. Same for all of these. Then for pi 2, all right, well, I know that pi 2 is going to be equal to, using my next, I'm going to have my 3 repeating variables plus 1 more of the non-repeating variables. It's going to be equal to d to the x2, v to the y2, times rho to the z2, times the density of air, rho a. Then if I plug in the dimensions, I will have L to the x2 times LT to the negative 1 to the y2 times ML to the negative 3 to the ML to the negative 3 to the z2 times ML to the negative 3, which is my density, the units for the dimensions again for the density of air, and that will be m to the 0, L to the 0, t to the 0. And so then L, I'm just going to create my 3 equations again, M, L, and T. This will be x2 plus y2, x2 plus y2, minus 3z2 plus 1 equals 0. Or, sorry, minus 3 equals 0. Minus 3 equals 0. And that comes from the minus 3 is from here, the minus 3z2 is from here. The plus y2 is from here, this term, and then the x2 is from here. M, I can get that z2 plus 1 is equal to 0. And then for time, I can say negative y2, well, that's just equal to 0. And from this, I get that y2 is equal to 0. From this, I get that z2 is equal to negative 1. And if we substitute these in, I will find that x2 is also equal to 0. So from this, if I put all this together, I get that the second pi term is simply rho A over rho. Rho A over rho. So again, a fairly simple pi term. Rho 2 is equal to rho A over rho. Oh, rho A over rho. Sorry, not rho A over rho A. That would be a violation of pi terms. That would not be appropriate. All right, questions so far? again, all I'm doing is I'm setting up my expression. I know the general form of it because I know what my repeating variables and my non-repeating variables are. Then I am taking my dimensions and substituting my dimensions in the place of each of the variables. And then all I'm doing is solving a system of linear equations in order to find the variables and then produce the final pi terms. So we have two more of these, pi 3 and pi 4. Pi 3, I just want to work through the whole thing. Pi 3 is equal to d to the x3 times v to the y3 times rho to the z3 times L. And then substituting in our dimensions, I get that rho to the z3 times L. This will be L to the x3 times LT to the negative 1 to the y3 times ML to the negative 3 to the z3 times, and again, this is just length, although it's kind of funny that our variable here is just length, and so, or distance from shore, I suppose, and that's just going to have, our little l is just going to have dimensions of big L. And then that is m to the 0, L to the 0, t to the 0. And then I can create equations for both the length, the mass, and the time. And I will have for the length x to the 3 plus y to the 3 minus 3z3 plus 1 equals 0. I will have z3 is just equal to 0 because there's only one z term that this occurs on, so it's just equal to 0. And t, I will have that negative y3 is equal to 0. So negative y3, no other time terms, so that's just equal to 0. And so from this, if I put all those together, I can get that x3 is equal to negative 1, z3 is equal to 0, and y3 is also equal to 0. So my final, so for my pi 3 final form is going to simply be L over D. L over D. And then one more. Bear with me. I do want to get through this example. I know I'm moving kind of quickly. I'm trying to cram a long form example into this lecture here. So pi 4, I'm going to have pi 4 is equal to dx to the 4th times vy to the 4th times rho z to the 4th times acceleration due to gravity g. And then this will be Lx to the 4th. Now, I don't know why you would include that as one of your variables. You'd think that would be a constant, but maybe I want to investigate waves on the surface of Titan or something. I don't know. There are bodies in the solar system that do have liquids on their surfaces. Very few, but the only one I'm aware of is Titan. There may be other bodies with oceans, but in terms of actual liquid flowing on their surface, large bodies of it, the only one that I'm aware of is the moon of Saturn, Titan. It's so cold, it has lakes and seas, literal seas of methane and ethane and other hydrocarbons. It's cold enough that basically natural gas becomes a liquid, and it just flows over the surface, forming canyons and lakes and rivers. It's the geography or topology of the moon Titan is actually very similar to the Earth. If you look up some satellite photos of Titan, it's amazing how similar it is to the Earth, not in terms of like shape of continents or something, but it has the very same erosion patterns and gullies and washes and everything else you'd associate with water, except it's not water flowing over rock eroding it. It is actually methane and ethane flowing over frozen water. And so the rock on the planet is basically ice, and the liquid is methane or ethane. But anyway, sorry, a little bit of a tangent there. We got to get through this quickly. Let me go on a tangent about Titan. Anyway.
Fluid?
Yes, it is fluid mechanics. So LT to the negative 1 times Y4 times ML to the negative 3 times Z4 times LT to the negative 2, T to the negative 2, equals m naught, L naught, T naught. And then if I create my equations from m, L, and T, this will be x to the 4th plus y to the 4th minus 3z to the 4th plus 1 equals 0. And z to the 4th, or c to the 4th, sorry, x4, y4, z4, not to the fourth. And then for t, I get negative y4 minus 2 equals 0. And if we take all that together, we can get that x4 is equal to 1, z4 is equal to 0, and y4 is equal to negative 2. And so therefore, my final pi term is going to be dg over v squared. That will be my fourth pi term. And then finally, so we're almost done. I'm just going to summarize everything once more with a final form of our relationship. So thus, here we have replaced 7 variables with 4, and my final relationship that I'll use to conduct my experimental analysis will be h over d is equal to some function of rho a over rho, comma L over D, comma GD over V squared. And that would be my final relationship that I could use to investigate these properties or this system. All right, I know I went through that fairly quickly. Thank you for bearing with me. This will be up for further review if you need to, but that will do it for today. So again, thank you. I'll see you on Wednesday, or we'll continue. We'll be working on maybe finding some functions, actually finding these functions, working with similitude, and that will do it. So again, thank you as always, and thanks for watching.